Well, hello guys. Today we gather together to discuss 5D parallelism in a nutshell. Um, and yeah, we're ready to roll. So let's briefly remind what we've been talking about and what is 5D parallelism. It's been, well, quite some time since our last meeting, so a reminder is due. Overdue, actually. And when we're talking about 5D parallelism, we mean first and foremost data parallelism. This guy. So, like, imagine that this is the tensor with our data. So this is our split in the batch size. Imagine like we have initially a huge batch, and then we split it in multiple mini batches and send these mini batches onto different GPUs. Next, tensor parallelism. Like this is our hidden dimension, and we split by the hidden dimension, meaning that, well, it's kind of I don't really want to uh reiterate the one of the previous lectures from start to bottom. But in a nutshell, we do a Weiss splitting of across hidden dimension, and then we do a few tricks for the matrix multipliers where we compute the matrix partials and then we add them up later on. Next, we have sequence and context parallelism. Um, and it's kind of, well, splitting across sequence dimension, and it helps us with processing uh, long sequences at various stages. So, sequence parallelism is mostly about computing the norms in parallel and context parallelism is mostly about splitting the attention across multiple GPUs. And at last we have, well, not at last, we have pipeline parallelism, which is um, splitting multiple layers of GPUs across multiple layers of the model across multiple GPUs. And this is different to tensor parallelism, right? So in tensor parallelism, we split hidden dimension. In pipeline parallelism, we split um, so it's like in tensor parallelism, it's like every layer is going to be split across multiple GPUs. And in pipeline parallelism, we're going to spread out different layers of GPUs, different layers of the model across multiple GPUs. So it's subtle but different. And at last, expert parallelism. Uh, I'm saying parallelism too many times today. When we have different experts on different GPUs. And by experts, we mean different FFN layers. And the next picture is, in addition to this kind of parallelisms, we can also categorize data parallelism into multiple strategies, which we call zero strategies. 0, 1, 2, 3. In 0, 1, we um, shard optimizer states. In 0.2, we shard optimizer and gradients, and in 0.3, we shard optimizer states, gradients, and parameters. This is a beautiful picture provided by Nana Banana, and we can see how, well, um, yeah. So green is the parameters. We shard the parameters first, then gradients, and then model um, parameters. And I said green is parameters. It's optimizer states. Yeah, my brain is not brainy today, so probably I'll be saying wrong stuff. Um, but bear with me, please. So, um, and before we dive any further, let's recall what is 0.3 and how exactly it shards the parameters. So basically, in 0.3, we shard parameters across multiple GPUs. And let's see, like, we can use GPU 0 and GPU 1, for instance. And then when we need to do any kind of computation, we shuffle the weights from one GPU to another. And then each one of the GPUs can do the computation with the weights that they send, that the other GPU sends over, do the computation, and then discard the weights. So at peak times, we would have increased memory consumption because we need to get those weights. Uh, but our kind of baseline is going to be lower. So we need to reserve some memory for the baseline, uh, for the parameters that we own, and we need to also reserve some memory for the temporary parameters when we need to do any kind of computation. And in the book, we have a nice comparison between 0, 3 and pipeline parallelism as a way to kind of shard the model parameters. Um, um, And the core idea is that with 0, 3, um, well, in both cases, we shard the weights, right? But the different thing is what we communicate. In 0, 3, we send over weights from one GPU card to another, meaning that each one of the GPUs processes the entire data stack, right? And it can potentially be different. Well, not potentially. It's different. It's different data stacks, right? So data slices. So on one GPU, we can have data slice A, and then we need weights to process this data slice A. On the next GPU, it's going to be data slice B, and we need another set of weights to process this slice. And with pipeline parallelism, instead of each one of the GPUs owning its own piece of data, the ownership changes. Now each one of the GPUs owns weights, and we shuffle the data around, meaning activations. And when I saw this table, the first thing that came to mind, especially since it says that in 0, 3, only a fraction of a layer is stored on each one of the GPUs, which is kind of which kind of contradicts this picture, right? So like, but I think that this picture is simplified version because we have only two GPUs. But if only a fraction of a layer is stored, then why? Well, and I have something in the chat, sorry. Oh, okay. Somebody dropped, no problem. Then why do we compare 0, 3 with pipeline parallelism and not tensor parallelism? And the answer is with the speed of communication. So, oops, with tensor parallelism, we need excessively high communication speed, and when we shard our training across large clusters, the bottleneck is within the isn't the communication, and as we can see in the picture, well, since tensor parallelism shards weights across every layer and requires a huge amount of computation. The link between different nodes with GPUs is just not sufficient. So the only place where we can do tensor parallelism efficiently is inside of a single node where we can use NVLink. And I'm not a hardware expert, but in my mind, NVLink is kind of like super high speed kind of hardware communication, direct hardware communication, like a highway, like super speed highway. And then we have like regular roads that connect different nodes with these NVLinks, and we can have only limited number of GPUs inside of a single node. I think it's 8. So this is kind of our ceiling, 8 GPUs across which we can do tensor parallelism efficiently. So this is the reason why, so like for this bottleneck, we either have to opt for 0, 3 or pipeline parallelism, and I think that pipeline parallelism requires less communication, or at least we can kind of interleave the communication stages more efficiently. So we'll see later that people usually opt in for pipeline parallelism instead of the 0, 3. And in the book we have multiple pictures to remind us about different parallelism strategies. So, tensor and sequence parallelism is basically splitting up once again the hidden dimension and splitting up the sequence length for different parts of the um, pipeline that our data goes through. And here we can see once again that tensor parallelism and context parallelism, for that matter, it's focused on, well, self-attention and FFN. And sequence parallelism is, well, mostly to do the layer norm thing. Um, yeah, FFN right here. And for the expert parallelism, it's kind of a natural way to parallelize stuff. We have multiple experts that are fairly small, much smaller than our regular FFN layer, and then it's a natural way to parallelize stuff, right? You just push a small expert onto a single GPU, or maybe onto a single node if it's still a huge expert, where we can do tensor parallelism, and there you go, kind of naturally parallelizable stuff. And the overall picture that we have in the book is, well, looks pretty. I'm not sure if it helps somebody who doesn't have a very good understanding of what's going on. But once again, we shout across hidden dimension. In my view, it's kind of maybe a prettier, maybe, well, prettier, but less understandable version of what we had in the beginning right here. So I'm not going to go through too much detail here because we've basically covered it already. Slice across hidden dimension, uh, mm, tensor parallelism that we can do for FFN, and for self-attention, sequence parallelism for layer norms, well, and for the router. Um, hmm, yeah, maybe. Yeah, I guess I'll need to get back to this and revisit it. I'm wondering why they How can we do sequence parallelism for yeah, I mean, it kind of makes sense, right? For the router, we don't need the entire sequence. Each token decides where to which expert it's going to be routed. So, kind of makes sense. Um, and the most interesting part, at least for me, is to figure out not only the theory, like how we can do stuff, but what is actually used in practice. And here we can see a few tables from the recent open and not only open, like from the recent models where technical reports mention parallelism strategies, and we can see the evolution of these parallelism strategies. So for Llama family, um, they started with the basic data parallelism. Then for Llama 2, uh, they evolved to one of the zero things. I'm not sure. At least I didn't find which one of the fully sharded data parallelism strategies they used for Llama 2, but at least they used something. And then we have a uh, much more detailed report for Llama 3, where they explicitly mentioned the 4D parallelism strategy. And we can see that there they used tensor parallelism for exactly 8 GPUs, which fits into a single node within the link. So this is our ceiling, and they efficiently use the ceiling, the number of GPUs that hit the ceiling. Then we have 16 splits of pipeline parallelism. Um, and I didn't dig deep into that, but in my view, probably it's like 16 splits of pipeline parallelism, and then each one of these splits is going to be sharded one more time into different tensors for tensor parallelism, but I might be wrong here. So don't take my word for granted. This is how I imagine things, at least. And they also go with FSDP across 128 splits. And we can see here that for Llama 3 and Llama 3.1, context parallelism differs from 1 to 1 to 16. And to my best understanding, it's because it's for different context length. So for short context length, they didn't do any context parallelism. For long context length, they had to kind of still fit in memory. All right, on to the next one. Google, Palm, Gemini family. So there, the picture looks fairly similar, right? So, well, they start with tensor parallelism straight away. Everybody, and this is a spoiler probably, but everybody does data parallelism. This is kind of the basic parallelization strategy, the foundation. And Google starts with tensor parallelism straight away. And the interesting part here that you can see is that there is no pipeline parallelism in any of the Google models, at least to the technical reports that we can find. Why? Well, if you look really close, you can see that hardware that the Llama, for instance, was trained on, it's GPUs, NVIDIA GPUs specifically, A100 and then H100. And for Google, it's TPUs. And the thing is that for GPUs, this is GPUs on the right, GPUs clusters. Uh, the high-speed bottleneck, we're limited in the number of hardware units that can do high-speed communication called NVLink up to 8. And this is like the single nodes. Like our ceiling for tensor parallelism is 8. But with TPUs, um, apparently, um, TPUs have some sort of kind of mesh network where each TPU uh, has a high speed connection to each one of the other TPUs, so they kind of all interconnected, and the communication inside of the TPU cluster is extremely efficient. It's called Uniform 3D Torus, direct chip-to-chip communication, and therefore they don't really have to care about pipeline parallelism. They don't have to solve this kind of bottleneck because they can efficiently do tensor parallelism across multiple and multiple TPUs. So, in my view, it's just a more efficient way to do training and more efficient way to parallelize. Uh, and it all comes down to the specialized hardware design in the first place. And now to DeepSeek family. Um, well, same stuff. We see tensor parallelism, we see pipeline parallelism, we see expert parallelism. And the thing that I noticed here is that we use 0, 1 instead of 0, 2. And let's get back to these slides with different zero strategies. So here we have 0, 1 and 0, 2. Um, 0, 1 is once again when we shard optimizer states, and 0, 2 is when we shard gradients. And the question is that when we do 0, 1, we can do, well, in terms of communication, amount of communication, we can get 0, 2 almost for free. So if we already shard optimizer states, we can just as well shard the gradients. Why not? So why don't we do 0, 2, which is, I think, is kind of the sane default strategy for data parallelism. Why don't we see it in DeepSeek reports? Well, and I'm not smart enough to figure it out on my own in the time that I had to prepare this lecture, but so I had to consult with Claude, and I think Claude got me a fairly plausible explanation. And the thing is that they already do pipeline parallelism, and they already figured out an efficient way of how to do pipeline parallelism. Additionally, they use not H100, they use H800, and I think that H800 has a slower NVLink speed, which means that the ceiling for efficient communication inside of the node is lower, and that kills the attractiveness of tensor parallelism for them. At least decreases the attractiveness. And since they So that's why we don't see tensor parallelism here. So uh, at the same time, going back to zeros, since we already done pipeline parallelism, uh, it seems that the math for them checks out to use only 0, 1, because when you do pipeline parallelism, each one of the GPUs already owns, well, say we have 4 GPUs, uh, owns only 1/4 of the model layers, right? And that means that they already store not the entire gradients, but they already store like 1/4 of the gradients. Each one of the GPUs already store the gradients only for the layers that they own, and that means that well, 0, 2 can chart these gradients, but does it make too much sense for them to do that? Well, it seems no. So they stick with 0, 1 because it's still probably a bit less complexity. You shard less things, so less kind of smaller surface for failure, and you already have enough savings from sharding the gradients because you do pipeline parallelism. So this is Claude's best understanding, and I don't have any objection to what Claude thinks in this regard. Let me know if you in the comments or like right now if you're on the call, let me know if you think there is any other way why DeepSeek can use 0, 1 instead of 0, 2. And this was pretty much it from my side. Do you guys have any questions?
No, thank you so much. It was wonderful.
Well, lovely. Thank you guys and see you next time.